Welcome to eMathsMaster Student Edition. This video shows you how easy it is to use eMathsMaster Student Edition and demonstrates what is included in the program. The platform is easy to access and the program can be used on all devices with an internet connection, like your mobile, tablet, laptop or desktop computer. Logging in is easy. Once you are logged in, you are taken to the student dashboard. This is your navigation center, where you can choose from lessons and assessments set for you by your teacher. You will find these on the left-hand side. Once you click on the step given to you, you will have a pre-step assessment, where you can answer a number of questions to gauge your understanding of a topic. You can then watch one of the 380 brightly coloured, professionally animated films that follow stories, lets you meet some interesting characters and uses real-world examples to help you become an eMaths master. Each module has been created by highly qualified maths teachers and covers the full maths curriculum from Key Stage 2 to GCSE, so you can receive the best maths education possible. After you have watched your film, you can complete the maths questions to make sure you fully understand what you have just learnt. The lessons and maths questions are an excellent revision tool. It really is as simple as log in, watch, learn, repeat. Once a session is finished, your progress is automatically saved and you can start back right where you left off. When you have completed a section, you can repeat the lesson as many times as you want, leaving no gaps in your knowledge. You can access eMathsMaster in the classroom, from the comfort of your own home, or even on the go, making revision quick, easy and fun. Students who are already using eMathsMaster have reported increased confidence in class, better learning outcomes, and more interest in the subject. So, what are you waiting for? Begin your lesson and start your journey to becoming an eMaths master. Teaching techniques. When asking pupils to consider whether an angle is acute or obtuse, I would ask them to think about whether it's greater than 90 degrees. They can use the corner of their exercise book or a piece of paper to make the comparison, so the corner of the paper is put into the apex of the angle. You can see clearly here that this angle is larger than 90, so it is obtuse. On this diagram, the angle is less than 90 degrees, so it is acute. Convert percentages into fractions out of 100. Percent means per 100, which means literally divide by 100. So if we have 50%, that is 50 per 100, which is written as 50 out of 100. And that fraction can be simplified to a half, because if we divide both the top and bottom numbers by 2, we get 25 over 50, and if we divide them by 25, we get half. 20% is 20 per 100, so 20 out of 100. If we divide both the top and bottom numbers by 20, we can simplify that fraction to give us 1 over 5. 26% is 26 per 100, so 26 out of 100. And if we divide both top and bottom numbers by 2, we get 13 over 50. There's nothing else we can divide both top and bottom by, so this is simplified as fully as it can be. Understand loci about a point, a line, and a corner. The locus of a point is the path traced out by that point as it moves, either through 2D or 3D space. Loci is the plural of locus when there is more than one. The first kind of locus we will look at is the locus of a point that moves so that it is an equal distance from another point at all times. If this point moves so it is always the same distance from this point, we see that tracing this path out forms a full circle around the second point. You could be asked a question like this. Draw the locus of a point that moves so it is always 4 centimeters from the fixed point P. For this, we need a compass and a ruler. We open the compasses so that the distance between the point and the end of the pencil is exactly 4 centimeters. Place the compass point at P and draw a full circle with this. The circumference of this circle is exactly 4 centimeters from the point P in any direction. The second kind of locus is a locus about a line. We have a specific line here. The line is made up of 2 points, one at either end. These can therefore use loci about a point. For example, we could take this point at the end. If we want to draw a locus that is 2 centimeters away from the line, we start by drawing circles around both of the end points. We now have loci of 2 centimeters for both ends of the line. Because the line is in fact connected, it is not just 2 points. We need to make sure the locus is 2 centimeters from every part of the line. We already have the ends of the line, which are 2 points. To do the rest of the line is quite straightforward. We measure 2 centimeters away from the line on either side and draw a line at this distance on both sides that connects the circumference of the circles. Alternatively, we can start by drawing these 2 centimeter lines on either side, creating a rectangular shape around the line. Remember to include the 2 centimeters distances from the ends of the line. Then, we draw our 2 centimeter circles at either end. Notice that we do not include the corners, here, 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 and here when doing it this way. This is because we already know that from the points at each end we need a circular shape that is exactly 2 centimeters locus from the point. It is very important that you do not include the corners, as it is one of the most common mistakes with loci. Our third type of locus is a locus inside a corner, or between 2 lines. We look at the 2 lines, here and here. We are asked for the locus of a point that is the same distance from both lines. This is the line down the centre, here. This is really the angle bisector, as we have the angle formed by the 2 lines, here, as we are bisecting by drawing a locus that is equidistant from both lines. Like other loci, angle bisectors are also done with a set of compasses. We have covered this in a previous lesson. Similarly, if we want a locus that is an equal distance from 2 points, we again want the bisector between these 2 points. We have also covered this in a previous lesson. Teaching techniques. When teaching this topic, you must reiterate that the numbers have to be in ascending order. So, that's from smallest to largest first, before you tackle finding the middle number. If you don't do this, you will end up with the common misconception of just literally looking for the number in the middle. It's also a good technique to either tick or cross the numbers off from the outside, rather than just looking at what looks like it's in the middle. If you do this, it will be a lot easier to work out how many numbers are in the centre, whether it's 2 or 1, and therefore what the median is. The next tip is, if you have an even set of data, so for example, here we can see that there are 6 different numbers. Once you put them in order, you'll find that you get 2 numbers in the middle. we need to add the two numbers together and divide by 2 in order to find the median. So if we put these in order, 12, 21, 43, 56, 65 and 90, we cross them out from the outside, 12 and 90, 21 and 65. You can see that we have 43 and 56 in the middle. Now this is a harder one to work out what the middle of 43 and 56 is. So instead we use the trick of adding them together and dividing the answer by 2. This gives us an answer of 49.5. So 49.5 is the median. This would have been very difficult to work out without doing this calculation. Deep thinking. Adam says that the median is 7. Why is Adam wrong? You can challenge misconceptions by showing students questions that are wrong, drawing out any problems they have. For example, here we can see that what's happened is they know the median is the middle number, so they've looked at the set of data and they can see that 7 is the middle number. What they've forgotten to do though, which is fundamental, is to put them in order first. So from smallest to largest we should have 2, 3, 3, 6, 7, 8 and 9. And now we can see the median number is actually 6 and not 7. This is the most common mistake that students make when finding the median. Simultaneous equations using a graphical approach. Review. Plotting the equation of a line. A straight line linear function forms the equation y equals mx plus c. For example, y equals x minus 2. To plot this line on a graph, we can use a table. We have a table of x and y values. As long as the x values represent values along the x-axis, we can put these in. Here we'll choose -4, -2, 0, 2, 4 and 6. Now we substitute these x values into our equation. X minus 2. These give us the y values. When x is -4, y is -6. When x is -2, y is -4. When x is 0, y is -2. When x is 2, y is 0. When x is 4, y is 2. And when x is 6, y is 4. Now we plot these coordinates on our graph. -4 minus 6 is the first coordinate. -2 minus 4. 0 minus 2. 2, 0. 4, 2 and 6, 4. We then join these up to form a straight line which has the equation of y equals x minus 2. When solving simultaneous equations, we draw both graphs. Here we have the graphs for y minus 2x equals 1 and y equals x squared minus 2. We can begin by rearranging this first equation so it looks more like the linear equation y equals mx plus c. So this becomes y equals 2x plus 1. We have y equals 2x plus 1 and y equals x squared minus 2. Plotting these onto a graph, y equals 2x plus 1 is this line, and y equals x squared minus 2 is this curve, because it is a quadratic and so forms this U shape. The solutions to the simultaneous equations are where these graphs intersect. We can see they intersect at this point here, where x is 3 and y is 7. This coordinate is our first solution. They also intersect here, where x is -1 and y is -1. We have two solutions because we have a straight line crossing a curve in two places. There are two solutions to this graph. Each solution has a pair of x and y values. Now we'll look at a pair of simultaneous equations, where one is the equation of a circle. Here we have x squared plus y squared equals 25, the equation of a circle, and y equals x plus 1, a linear equation. Plotting the equation of a circle, we need to remind ourselves that the equation of a circle is x squared plus y squared equals r squared, where r represents the radius of the circle. So if r squared is 25, then the radius of the circle must be 5. From the origin, we go out to 5 in each direction and then join these points up using a compass to form the circle. We then plot the line y equals x plus 1. We can see the points at which the line and the circle intersect, giving two solutions to these simultaneous equations. All we need to do is read off the coordinates of these points, giving us the x and y values for each coordinate. This gives us the exact points at which we have solutions. The first point we can see is at 3, 4. So the solution is x equals 3 and y equals 4. The second point is at -4, -3. So x equals -4 and y equals -3. These are the two solutions where the line intersects with the circle. Teaching techniques. There is a quick way of doing this on a calculator. For example, if this sequence is determined by the term-to-term rule, un plus 1 equals un squared minus 7 un plus 4, given that un is 2, we can find u2, u3 and u4 on a calculator. We can do it using the long method, where we replace and substitute in the previous answer into the equation each time to get our next answer. Or we can use the answer button on a calculator. For example, when un equals 2, we type into the calculator 2 equals. Then we type in answer squared minus 7 answer plus 4. Press equals and you get -6. If we press the equals again, the calculator stores the function, as in the equation we need to use, and re-inputs the previous answer, giving us 82, and then 6,154. This is very easy to do. However, I would always show students the long method first, so that they understand the substitution and practice that skill in itself, before showing them the calculator method. If they get the calculator method wrong, they have no working out at all that would gain them marks in an exam. Deep thinking. Tony is asked to work out U2, U3 and U4 when a sequence is defined by the term-to-term rule un plus 1 equals un squared minus 7 un plus 4, given that u1 is 2. This is what Tony works out. u2 equals 2 squared minus 7 times 2 plus 4 equals -6. u3 is -6 squared minus 7 times -6 plus 4 equals -74. and u4 as minus 74 squared minus 7 times minus 74 plus 4 equals 5,998. Explain what mistakes Tony has made. Tony has correctly substituted in the first value of u, 2, into the equation. He's done 2 squared minus 7 times 2 plus 4. That's 4 take away 14 plus 4. If we type that into our calculator, we get minus 6. So this is correct. He correctly substitutes into the equation minus 6 to replace the u. He has written minus 6 squared minus 7 multiplied by minus 6 plus 4 equals minus 74. When we type into our calculator minus 6 squared, we have to be very careful because on a lot of calculators, if you simply type in the function, it will give you minus 6 squared equals minus 36, where in fact we know that minus 6 squared is minus 6 times minus 6, which is positive 36, as a negative times a negative is positive. We should have 36 minus minus 42, and we have plus 4. This gives us an answer of 82. This is a very common error that students make. They simply type it into their calculator, as they've written it without thinking about BETT or how the calculator works. First of all, we need to consider the minus 6 squared on a calculator. It should be typed into a calculator as brackets minus 6 close brackets squared, which is 36. Or they can just think of it as 6 squared, because negative 6 squared is the same as positive 6 squared. They then need to do this as a separate function for 7un, which is minus 42. They are subtracting that from the negative 6 squared, and when we subtract a negative, we end up with a positive. What they are actually doing is 36 plus 42 plus 4, which is 82. This is where Tony has gone wrong. Highlighting this type of calculator error is very important, as students who understand how to substitute and iteration often only make mistakes because of their calculator knowledge and understanding of negative numbers. Teaching techniques. Start with simple exponential graphs in the form of y equals a to the power of x. When the variable x is the power, it makes an exponential graph. For example, y equals 2 to the power x. Y equals 5 to the power x. Y equals 15 to the power x. There are some key features to these graphs. Firstly, they start steady and they grow quite rapidly. There are two other key features of these graphs. We're going to look at where this graph crosses the y-axis. In this example, it crosses here, where x is 0. I'm going to substitute that into the equation y equals 2 to the power x. So y equals 2 to the power 0. Anything to the power 0 is 1. Therefore, this curve intercepts the y-axis at 1. Looking at this example now, it crosses the axis here, where x is 0. So we have y equals 15 to the power 0, which again we know is 1. So the curve crosses the axis or intercepts the y-axis at 1, and similarly with this question, y equals 5 to the power 0. Again, y equals 1. So, an equation in the form y equals a to the power x will form a graph that crosses the y-axis at 1. What happens when the values of x get smaller? For example, if we look at x equals -3 and we substitute that into the equation y equals 2 to the power -3, this is 1 over 8, 1/8, or 0.125. So, what happens is that as the values of x get smaller, the graph approaches 0 but never actually touches it. We say the x-axis is an asymptote. Graphs in the form y equals a to the power x, when x is less than 1, are also exponential graphs. They also cross the y-axis at 1, but they fall steadily. Again, the x-axis is an asymptote. So, to summarise, an exponential function is where the x value is the power. It forms a graph that rises quickly. It crosses the y-axis at 1, and the x-axis is an asymptote. This is a typical GCSE question. The graph shows the function of y equals a to the power x. Write down the coordinates of the point where the graph intersects the y-axis. It intersects here, at 0, 1. We can see that clearly. We also already know that all graphs in this form will intersect at 0, 1. This is because x is 0 and x is the power, and anything to the power 0 always gives us 1. Moving on to part B of the question, find the value of a. To do this, I need to choose a second coordinate on the line. I can choose any coordinate at all. I'm going to choose a simple one here, 1, 3. I'm going to substitute the values of x and y into our equation. Y equals a to the power x. We know that y is 3 and we know that x is 1. So 3 equals a to the power 1. A must equal 3. I can check this with another coordinate. For example, this one here, 2, 9. I think that a equals 3. Therefore, the equation should be y equals 3 to the power x. I'm going to substitute in the value of x and see if it gives me the value of y. Y equals 3, and in this example, x is 2. So y equals 3 squared. Y equals 9. Yes, it does, and therefore I know that I've got the correct value of a. In this example, the equation is in a slightly different format. Y equals pq to the power x. As q to the power x is being multiplied by a value, it won't necessarily cross the y-axis at 1. To find the values of p and q, I need to start by finding out where it does cross the y-axis. If I look at this example, I can see the curve crosses the axis at 0, 1/2. I'm going to substitute these values of x and y into this equation. So, y equals pq to the power x. Y equals 1/2, which equals p times q to the power 0. We know that anything to the power 0 equals 1. This is the same as 1/2 equals p times 1, 1p. So p equals 1/2. I'm going to use this and the second coordinate to find q. The second coordinate I'm going to choose is this one, 1, 2. I could choose any coordinate I liked on the curve, but I'm going to keep the numbers simple. I'm going to go back to my equation, and instead of using p, I'm going to use the value of 1/2, which I calculated before. Y equals 1/2 times q to the power x. Substituting in these values, y is 2, which is equal to 1/2, multiplied by q to the power 1. This simplifies to 2 equals 1/2 q. Therefore, q must equal 4. So, the value of p is 1/2, and the value of q is 4. Teaching techniques. When teaching this topic, you need to be sure students fully understand why a scale factor needs to be either squared or cubed for area or volume. This can be easily demonstrated using a diagram. For example, we can show a 1 cm square. This is 1 cm by 1 cm. We can also show a 3 cm square, 3 cm by 3 cm. We see from the lengths that the ratio to go from the smaller 1 cm square to the larger 3 cm square is to multiply by 3. The scale factor, k, equals 3. Now looking at the areas, we see the area of the smaller square is 1 cm squared. We can work out that the area of the larger 3 cm square is 9 cm squared. To get from 1 cm squared to 9 cm squared, we multiply by 9. Comparing the relationship between these multiplier values, we can see that 9 is 3 squared. Therefore, when we find the scale factor for the length dimensions, we need to square it to find the scale factor for the area dimensions. It often helps to remind students about the units here. Length is recorded in centimetres. Area is in centimetres squared. Volume is in centimetres cubed. This helps students remember that we need to square a scale factor for area and cube it for volume. Now we'll try a volume example. Here we have a 1 cm cube and a 2 cm cube. We see that to get between the lengths, we need to multiply by 2. The scale factor is 2 for the length dimensions. Now we work out the volumes, which are base times height times width for a cube. So this is 1 cm cubed, and for the 2 cm cube, this is 2 times 2 times 2, which is 8 cm cubed. To go from 1 to 8, we need to multiply by 8. Again, by comparing this relationship, we can see that the relationship between the scale factors is 2 cubed. Therefore, we need to cube the scale factor for the length to find the scale factor for the volume. Deep thinking. A and B are two similar solids. The volume of A is 3 centimeters cubed, and the volume of B is 81 centimeters cubed. The length of one side of A, shown in the image, is 2.2 centimeters. Calculate the length of side X. Ben says the answer is 81 divided by 3, which is 27. 2.2 times 27 equals 59.4 centimeters. So X must be 59.4 centimeters. Explain why Ben is incorrect. We'll start by looking at what information we have. We can see straight away that we have a pair of volumes. To find the scale factor, we divide 81 by 3, which gives us 27. So we can see Ben has done this correctly. This is the volume scale factor. The scale factor K cubed is 27. We want to find the scale factor for the length, which is K. We need the cube root of 27, which is 3. The scale factor is therefore 3. Now we multiply 2.2 by 3, which gives us an answer of 6.6 centimetres for x. We can see that Ben does not have this correct. What mistake has he made? He has correctly identified the scale factor between the volumes as 27. However, he has then simply assumed that this is the scale factor. He has then multiplied this by 2.2 to get 59.4. What he should have done is square root the volume scale factor to get the scale factor for the lengths, as these are not the same thing. This is a common misconception for students to have, that scale factors relate to lengths, areas, and volumes in the same way. In fact, they do not, and students need to be reminded that if they find the volume scale factor, they must cube root it to find the standard scale factor for the length, or square root it for the area. This film demonstrates how eMathsMaster Teacher Edition can be used as a teaching aid, classroom tool, and revision program that helps schools, teachers, and students achieve the best results possible. eMathsMaster is used in primary and secondary schools and further education colleges to create maths teaching capacity. eMathsMaster enhances SATs preparation in primary schools and helps secondary and FE colleges achieve improved GCSE results with a minimum Grade 5 guarantee for all students that complete the programme. Each of the 380 modules in the eMathsMaster programme includes a professionally narrated animated lesson, an assessment, and a set of maths questions. The Teacher Edition also includes 380 teaching techniques sections to increase confidence in teaching maths. Teachers can use eMathsMaster Teacher Edition as a teaching tool to deliver high-quality maths lessons and to expand students' learning both inside and outside the classroom. eMathsMaster Teacher Edition is suitable for maths teachers, newly qualified maths teachers, and teaching assistants. Prior to delivering lessons on a particular topic, teachers complete the teacher training for the relevant topic. The Teaching Techniques films provide teachers with the pedagogy needed to deliver great maths lessons. These films include real-world examples, demonstrates engaging classroom activities for the lesson, helps students develop reasoning, enhances deeper thinking, and covers common student misconceptions. The teacher is then confident to deliver the topic in class. The pedagogy used in the eMathsMaster products has been created by the Dean Trust's Teacher Training School at Ashton-on-Mersey, and this technique is used by many schools using eMathsMaster. Using eMathsMaster in the classroom is easy. Utilising a projector, video screen or interactive whiteboard a teacher would show their class one of the bright, colourful and animated lesson films. These films cleverly combine narrative with the mathematics to create an engaging learning experience. Ideally, sound should be enabled for these films, although, as there are subtitles, sound isn't a necessity for the learning process. When the film is finished, the teacher can take the class through the system assessment on screen and help students answer maths questions as a group or allow them to do so through individual learning. Each teacher can customise eMathsMaster to best meet the needs of their classes. For example, it is easy to create additional assessment questions. Teachers can discuss with students or expand on the topic if they wish. Once a teacher is confident the class understands the topic featured in the module, everyone moves on to the next module on the system. It really is as easy as log in, watch, learn, repeat. At the end of the class lesson, the homework for the students is to repeat the modules covered in the lesson on their own eMathsMaster student editions. They would watch the film, complete the assessments, and answer the maths questions. This could include additional questions that the teacher has set as homework on the system. The system ingeniously combines class participation and peer learning. As well as this, students can use eMathsMaster at home and on the go. eMathsMaster can be used in many ways, meaning that it is adaptable and suitable for the wide variety of learning needs. Using eMathsMaster as homework is a fun way to encourage students to do individual revision. Teachers also have access to the admin side of the learning engine. This showcases great reporting and monitoring tools, easy class and team management, and has new functions and improvements always in development. The new and improved user side has larger videos for all users, a clearer course breakdown, as well as user-friendly assessments. eMathsMaster is always looking for ways to make learning maths easier than ever. eMathsMaster enables the teacher to keep track of all their students' results and progress in real time through one easy dashboard, reducing the need for heavy marking loads and giving the teacher the freedom to focus on what is important: student progression,